Please put your hands together to welcome to the podium John Walker to present his talk.
Evening, ladies and gentlemen. Thank you very much for the welcome. I had this scheduled for a bit later in the year and was asked to bring it forward. So I've been working on the presentation. I think it'll hang together fairly well, and I really want to explain why Dr. Joseph Owangi and I, Joseph is in the audience tonight to listen to this presentation. He and I have worked together for the last 10 years, mainly with civil engineers doing this same sort of thing. I was introduced or sort of requested to do some mine engineering or surveying for mine engineers a couple of years ago as some courses changed at Curtin. I think you've found out most of the things about me. I suppose I'm a dilettante. I never stick a job for a long time. I was 17 years in air traffic control, but I changed jobs every couple of years. But one of the proud things I've got is electronic engineering and the CAT buses that run around here. I was on the initial team where we put it together, and some of you blokes will probably know Peter Clifford of TerraVision with his mind map software. I don't know where it is now, but I worked for Pete when he was bringing mind map into 32-bit Windows environment and things like that, and had a lot of geologists working for him. But we branched out into vehicle tracking and things like that, and I came on with the vehicle tracking, and the Perth CAT bus was the first one we did. And I think from signing the contract to getting the bus going, we got 16 buses, 65 bus stops going in 8 months, and the buses weren't in Australia when we started, so it was all hands on deck. However, getting away from that, Joseph and I had worked for about 6 or 7 years with course notes and practical tasks, and sometimes we weren't getting as far as we could with getting the message across to the civil engineers of what surveying was about. So we changed the course a bit, lecturing, running workshops, then running practical sessions, because the course was only a half semester, so we were only getting, of the 25 credit points, we're only getting 12.5 credit points. So we're only doing about 3 hours of student contact a week. We changed that around, and we found that running a workshop allowed us to get through what the next task was going to be, so that they could, students could come out into the field and know what they were trying to do, and basically have to manipulate the instruments, take the recordings, and then plot the results. I wanted to start with this because when I started 2014, I was also running civil engineers at UWA in a postgraduate course on surveying for civil engineers, and we just happened to have the mining games on. And so I was invited across to help with the mining games, and when I saw this, I thought, yeah, we might have to teach some of the mining engineers about surveying, because this is not quite, well, sorry, I haven't worked underground. Maybe this is normal for underground, I don't know. Maybe, well, the way Chris was carrying on, I think he's got good clearance there as well. But I thought, you know, this is the sort of thing that we really don't want to do. So Joseph and I came up with this book, Surveying for Civil and Mine Engineers, and we wanted to turn the thing around. We all, civil surveyors, mine surveyors, they have a course to go through, but we were just trying to look at the flip side of the problem of what did we think an engineer should know about surveying, so that they can make informed decisions when they do talk to surveyors, and don't get a whole lot of rubbish from a surveyor using big long words that probably the surveyor's a bit vague about at the best of times anyway. So we put this up, but part of it is why employ surveyors. Chris said a mining engineer will never touch a theodolite, but you know, you get some of them as young and silly, they might be game. And so we presented a series of presentations associated, or to make it work, you have to have a scenario. So we said, righto, we need a number of exercises. What are we going to do? We'll get a little mine site and we'll develop the mine site basically from greenfield to where we want to be with it. Obviously not closing it down, but we said, all right, we've got to have a mine site. The first thing we've got to do is bring levels onto it. We've got to put level control in. And then I got a brainwave, rang AusIMM a few years ago, talked to Peter, someone, I think, your education officer, and he said, well, if you've got mining engineers, the first thing you do is try to blow them up on a blast grid, so get them to do a blast grid over your site. Oh, great, so 6x7 blast grid over the site. And, sorry, going back, why surveying skills for mine engineers? It's part of professional development. I looked at what a mine engineer had to be responsible for. And of course, the mine engineer is responsible for site safety, development, all those things, is also ultimately responsible for the survey and making sure the survey is done correctly, because the mine engineer's going to sign off on the survey. The mine surveyor can sign everything he likes, but he's sort of free and clear because it's the mine engineer who's going to carry the can. So it's the ultimate responsibility, and it's also knowing the surveyor's craft, so that if they are talking to you, you've got some idea of what's going on. So we put in 5 survey tasks. We'll bring vertical control onto the site. Remember, I've only got an hour a week with the surveyors with the engineers for practical work. We've changed that round. We do 2 hours a fortnight. So that's why we had the workshop, so that when we do the practical, we can go straight into the field, do 2 hours work, get out and work from there. So we put in 5 tasks. We want to bring vertical control onto the site, which introduces people to the level, the idea of testing the level, working to tolerances and putting some levels in for next week. And so the next fortnight, measuring a ground profile and features using a drilling grid. So we've got some control up there. We put it in and said, all right, let's put a 6x7 grid in. How do you do that? The skills of actually laying out a grid, having laid the grid out, now we'll go through and take those readings. And part of this was also to supply data to the students to put into a GIS system, and I don't know which one. I think they were using ArcInfo or something, where they really should have been using SERPAC. Do we call SERPAC a GIS? I suppose we do we? It's a geographic information system, very specialised, I suppose, to mining, but it's still a GIS, a geographical information system. So that would give them their first part of data, so that when they go and do the GIS part of their course, they've got their own data to work with to see real work. It's no use giving anyone a file. Learn nothing from a file. You've got to go and do the work yourself. We said, all right, well, we like the look of this little site. Let's develop it. Let's put some control in, because mines need control. We've got a couple of control points near the mine site, and we will bring control up onto the site. Okay, so this now starts working with total stations. It starts working with EDM, and it now starts 3-dimensional work. We can get height from zenith angle and slope distance. We can get position from azimuth. So we're bringing that onto site, and we want to determine the grid orientation. And at this stage, we're starting to introduce the concept of a mine grid, a local grid, and the map grid of Australia, and how the 3 fit together. So at Curtin on our site there, I've merely translated the map grid of Australia to the Perth coastal grid that we're all familiar with, or there's the Goldfields grid at Kalgoorlie or wherever, there's the local grid. so that we can apply plane surveying techniques rather than have to work on the ellipsoid. And what I've done with these students is then, because there's 4 or 5 numbers in the grid, I've just dragged them back to 3 or 4. So we've got something like, the position is, this is 327 metres and, 1,500 metres north. So we've got a very localised grid, bringing it back onto a nominal plane grid, and then we can go back to the map grid of Australia. So that was establishing mind control and determining grid orientation, because my scenario is, there's a couple of control points out there, but once we start the job, sorry, you don't have those control points anymore. They've been bowled out by a bulldozer, or they're outside the work area and you've got no more access to them. So you've got to provide some orientation. And of course we have to do this on a mine site where you have your control and a minimum of 250 metres away, according to the mine surveyors stuff that I downloaded the other day. You've got to have a baseline about 250 metres long. So we generate a baseline so that we've got azimuth control for our grid. Then I said the 4th thing to do, which is their 4th practical exercise, is to place tertiary control on the mine site. Sorry, the established building control set out. Where I put my control point was really good. We put some drill holes in, we've got some really good results, and hell's teeth, where I've put my control point, we're going to flatten it because there's some unobtainium in there that I've got to get out. So we now need to put in some tertiary control to control buildings and set out things like that. So that's the 4th one that we do. We do a simple adjustment so that we've got the best fit for the points that we're putting in. I've got some drill holes up there. We'll measure where the drill hole collars are. The drillers have been in and they said we've hit a seam at 9.5 metres down and 7 metres down and 8 metres down. And so in the 4th one there, we've been able to establish drill holes. We've now established a seam. And so we can take that back into the GIS and we can look at our inclined planes, our dip and our strike. And I cover that quite a lot in the book because dip and strike is never covered very well in survey books at all. I've only got 2 references out of about 50 survey books that will actually cover it, and yet it's quite a simple concept. And then eventually we will have an exam at the end of the time where we calculate a circular curve. I mean, mines have always got curves on them. You've got to design roads and things like that. And in this case, instead of having a 7 or 8 metre road, I work on a 30 or 40 metre haul road or something like that to try to give an idea of scale. So we're always trying to put forward practical problems that have to be probably solved in the real academic world. So that was our site, building 204 with the engineering building, the library up there. There's 100 metres from there to there, 50, 60 metres wide, and we were eventually working on that area there where we would put a mine grid. You can see the local coordinate system that I have in there. These CEMs were just pegs that I put in the ground so that the students had to find the peg, do a site plan so that they could find the peg next time when they did it, because they would have the coordinates of it. And the first exercise was a couple of things. We did a collimation test to make sure the level was working correctly within tolerances, that it didn't have errors in the line of sight. We then did an open traverse, and I'm just getting used to this, from here up to a control point up there, a temporary benchmark. Now, and also we've got a bridge across there, that's a portal. How do you find the height of a portal? There's I need 3 metres clearance for the material, for the machinery. does that portal meet it? And then we wanted to bring control in, so starting off at a control point, coming down, winding up somewhere else to between two control points, so that we could then do a closed loop traverse, which would allow us to see how well we had performed the survey. Did I get within 50, I'm allowed a tolerance of 15 millimetres around the circuit, did I achieve that? If I didn't achieve it, what do I do about it? And so this was the closed traverse. And this was the first one because that one then allowed us to have control for the second stage, which was the blast grid. 6x7, which I'm reliably informed is a grid dimension. Is that right or wrong? Okay, happy enough? Okay, not every student did that. We then had to split the teams because I'd be running about five teams of 4 students for this. So we give them a couple of lines to do. They could collate that data, then they would have to share the data with someone else, which is all part of probably the team building thing that we're trying to get people to work together, to share the data that they've got. And then when you do that, you've got to make sure your work's all right because you're going to hand it over to someone else. And if they don't trust you, well, the whole thing's not going to work. And we said, all right, in the area, how many trees in each grid square or something? We were not going to position the trees. How many trees, how many appurtenances of some sort? So that they've just got the idea of picking them up, of doing the field work. Now that's assigned about 2 hours. And with all of these, they did all this recording work, but the amount of work they had to do at the end of the day to do the computations, to get the results, was probably not much more than they'd spent on the exercise. We didn't do an exercise like this and then I expect them to spend 10 hours on sorting it out. One of those, the work they did, I could probably whiz through it in about an hour, so 2 hours for them. And the students, we're in contact with them 3 hours a week, so we expect 3 hours back from them. That's part of the contract. So there was never any heavy work on it, it was just getting through it. So that then got the blast grid out of the way, and they could take that data then into their GPS, their GIS, and we've got a bench running around there at about 15.5 metres or something like that. What volume, if I put some batters in my GIS and I excavated down to the bench, what volume? What volume of drill hole? How big a drill do I have to use? I've got no clue. What size rotary drill do we use there for blasting? If this was blastable ground? What, do we use a 10-inch or a 2-inch or a what? You know, they're the questions. Kids, what size drill do we use? How much do you pull out of the ground? You know, how much spool have you got to go back in? So we were looking at that. And from that, that's roughly what the ground looked like with the levels. And from there, if we're going down to the bench, we can calculate the volume in various methods. We can use the contour method of volume, or we can use the depth method from each corner. And so those things are sort of done to death in the book of how they're actually worked out. So that would go into the GIS for them to pull it out. The third one was, now let's get some control into place. So I've got 2 control points there. They're in my local coordinate system, which have been tied back to the Perth coastal grid, which have been tied back to GDA, Geodetic Datum of Australia. Those 2. And so we said to them, well, here's some points here. They're about the coordinates. We had a surveyor run round and bang some pegs in and get some rough coordinates. And so what the students are expected to do is then work out when they're assigned to one of these points, if their group is assigned to one of these points, All right, you have to work out the rough bearing from your control points, CEM5 in this case, to 705A, so that when you're pointing at 705A, you can actually dial that into the total station. You then have orientation. We put a reference object, an RO, which was the side of the building here, and so when they come back in the field the fourth time, because they can't see 705 and see 400 because bloody bulldozer's gone through them, they've still got an RO. They've calculated a better position for CEM5 because it was only rough. They've then able to calculate an accurate RO, so that then gives us our mine grid orientation. And that was basically that exercise. Record the points so that you can do your station diagram to come back to it next week and basically find out where I am. And CEM5 was part of the initial level traverse that we did, going back to the known coordinates and height of 705A and C400 there, doing a zenith angle and difference in height. How did my level traverse compare with what I did here? Again, the idea is to show that there's more than one way of finding out an answer to any problem. Surveyors are very funny people, always employ a lazy person because they find the easiest way to do it. Except Chris has got a bad story about that. But there are more ways of solving a problem than one. Okay, so this is the third practical. We've established our control. The fourth practical, we go up, set up on the control point again, but now, because we've found out where our 3 drill holes are, and it looks as though we might want to actually use that position, we're going to lose our control point, but we need a bit of extra control because we're going to put a structure there or whatever we need it for. So we then go and do a small survey from the unknown point. We've got our bearing up there, and we do a triangular survey around there and use what we call the Bowditch adjustment to get the best position for the coordinates. So the tasks are to set the grid bearing to the RO. We know what it's meant to be. Align the total station to it, tap the numbers in. We've now got it lined up. Measure the bearing and the zenith angle and the slope distance to the 3 drill holes, and then it's measure and adjust the triangular traverse, because what happens in this one is that we set up there and everything's aligned, so that's why we read the 3 drill holes to find where they are. We've got 2 reflectors on A and B, and it then involves the students, or involves taking the total station from here, putting it here, and then so we're reading these angles and directions with a reflector there and the reflector there. Then we move the total station from there to there, and this is known as the semi-forced centering method of doing a traverse. So we've measured the 3 sides independently, and we can adjust it because we know we've measured angles and all those sorts of things and distances, and we can come up with a set of coordinates. The 3 angles have got to add up to 180 degrees. If they don't, we then have to distribute the angles through the traverse and then adjust from there on in. Okay, so that's the 4 things that we do. So from the mine site, and we will have generated, in doing this, we will have generated levels for A and B that we'll say, all right, that's our mine level system, until we get someone to come through and bring it back to the Australian height datum. It'll be roughly right, but we'll eventually want to tie it down. So they're done. We've now got our 3 sets of drill holes, and so we can now put that into a GIS, and we can work out the dip and strike. And you guys will all know how to do this better than I can. but I've got some techniques anyway. The dip and strike, that's what we wound up with. That's where the drill holes were, and I've worked out the coordinates of them because we have bearing distance, and we get a apparent dip angle there and an apparent dip angle, and this is solving it graphically. How do we find the strike and the dip using the graphical method? So in the book I've done this drawing. That was what we wound up with the horizontal plane and the dipping plane. And then the other day, because I love Douglas protractors, I thought, well, a Douglas protractor is a pretty good thing to do this on. If you've got one, you can, in the field, you can actually do this in your field book, and before you leave the field, you've got a pretty good idea of the strike and the dip of an inclined plane, if that's what you're after. I did a bit of this work when I worked on the Wollongong Dam, and we had to do a lot of dimensional blasting because of the ground there. There were lots of rocks that had seams in them, and you'd have to set up the theodolite on the top of the rock, find out the strike line, and then work out what the dip was so that the guy could bring a drilling rig along and drill down 2 or 3 metres to do a bit of it, so we could pop the rock off the top of a seam, because the Wollongong Dam was a notoriously difficult place to work. The main contractor actually made his fortune out of that because of the dental concrete that they had to do, because there was this 50 square metres of dental concrete, and by the time they got there was about 5,000 square metres of dental concrete, and it had just been slipped in as a nice little extra in there, and by the time you'd multiplied it by 1,000, they'd made a fair amount of money from dental concrete, because they had to get a stable base, because the Wollongong Dam, geologically, they looked at it, I think, in the 20s, and it really wasn't a good place to build a dam, but we needed a dam, and with more modern techniques it was put in. And so I worked on that from, well, I think we were there, I was with Bell Brothers, put the curtain in, and it was quite interesting working on the dam from a survey point of view, setting it up. Anyway, so that was just introducing dip and strike and how I've handled it in the book. I've also handled it mathematically. The fifth thing was an exam. What have we learned? How can we test people? We're trying to do a lot of things. You notice I haven't said anything about GPS yet. GPS for mine work, for precision mine work, leave it to the surveyors. There's things, there's RTK, there's $50,000 GPS sets and stuff for positioning and everything else. Leave that to the idiot surveyor with the adjustment programs. But the handheld GPS, now that we're used to working to a couple of metres, and even your telephone will do it, we tried this thing, well, we want to show the engineers what you can do with a handheld GPS. We also want to see how well, perhaps you've learned something like setting out a building or whatever. We want to see how you design a road, or what the parameters are that when you design a road, what you have to do. So we thought, righto, let's set out a road. Road was that we actually, on Edinburgh Oval, we set a whole number of them up, so they're all about the same, 30 to 25 metre radius. So R7, which is, or the one that I've circled, the road you see comes in like that, bends to 125 degrees, comes out. So the idea is to peg it around at 10 metre intervals. Set your theodolite or your total station up, peg it out using a total station and tape. Having pegged it out, now what techniques do we use to check how good our work is? And so the technique we use is measuring the chord distance between that chord and that chord, because they're 10 metre arcs. It's slightly under 10 metres. Now, if you get 9.95 metres or whatever the chord distance is meant to be all the way round, then you know the curve's been set out correctly because the numbers fit. But if it wanders in and out, then you haven't set the curve out correctly. We then come back with the GPS and measure the set out points, and the point of curvature here and the centre had been set out with the GPS to start with, so there's all sorts of movements going on. What sort of misclose am I getting at the meter, and the machine only reads to the metre anyway, what sorts of miscloses am I getting with it? And so the data that we've got on the top, the road 4, is the coordinates in MGA, which is of course what comes up on the screen of the GPS, and there was the chainage points, the direction and the distance to the chaining points as setting it out. Now, setting that out is no different from setting out a square building or something and measuring diagonals to make sure it's square. So nothing too horrendous in that. On the bottom, I've got a drawing that I presented to them. This is a bit of a haul road out of a Caterpillar handbook. Yeah, they're that big. And because if mine engineers, especially undergraduates, haven't been out on site and seen them, then they just don't appreciate the scale of what's going on. So we put those in, and they had to actually calculate curves like this, but we're real nasty. Every student gets a different curve. So that you might be able to help each other, but unless you're the smart person that's written the Excel program and flogged it to your mates, you're all going to have to calculate it by hand. And so in that case, we have a road something like this with you know, formations and shoulders and things like that in a centre line. No one gets the centre line, but you'll get the left and right offsets to calculate around the curve. So that was what we were trying to do with the course, and we can get through that, and we think that it's worked fairly well. Right. So the conclusion of we tried to provide survey theory and practical work methods for the engineers. The individual workload wasn't meant to be too onerous. We wanted a realistic scenario of what was going on so that they could gain practical skills and observational skills. Put the results or get the results in fairly simple plain geometric terms. Make critical decisions about your field work. Is the work good enough or not? Do I meet specifications or not? If the surveyor hands me this with these tolerances, do I pay his bill? Or do I tell him to go and do it again? If he's just missed the tolerance and it's not important, maybe we'll pay his bill. If he's missed it badly, well, he's just got to go and do it again. I'm sorry, you know, I'm not going to sign that off because I, as the engineer responsible, am not going to take responsibility for your crook work. We wanted to carry the results forward into a GIS unit and make critical evaluations. Can I do a simple task that might keep the site running? I put this to Chris and he said, Christ, no, we'll get the surveyor in a hurry from Perth in a jet. But, you know, when do I get the mine surveyor on site if I don't have him? Looking at the amount of survey work on an active mine, you've got the beggar there anyway because you know, it seems as though they're doing an awful lot of work by the time they get the data and put it onto plans and keep plans up to date. I mean, I think there is a lot of work there. I've done a bit of extra work. We were talking about sloping sites, so mere idle curiosity for me, and I won't bore you too long. I've got a slope and I want to put a circular pad on the slope. How much room does it take up? How do I calculate volumes? Because I go to any textbook, I can't find any of this. And it was the strike and dip work that I worked with that allowed me to develop it. So if I put a pad on the strike, the pad's on the strike line there and comes forward of a certain radius, that's where the toe of the pad is on the particular slope that I've got. And it covers a fairly big area. If I go around and then come here and put the pad on the strike line, I've got cut there, I've got fill there. How much is how much? And especially if I've got to do things like compaction every 200 or 300 mils. How much compaction do I have to do? How do I work out volumes and areas? And the last one, because I came off the land and I'm interested in them, the Turkey Nest Dam. Everyone says, well, you want to build a Turkey Nest Dam, you get a bulldozer operator and say, build a 5-acre dam. And he goes and builds a 5-acre dam. But I thought, well, yeah, there must be a bit more to it than that, but I can't find anything. So over the summer I sat down and ran through the numbers. And so now I've got an idea for me how to do this. Whether anyone else is interested in it, I don't know, but you know, it's just something for fun and entertainment. And the last one thing we're doing, this is more modern. Andrew Jaros from Kalgoorlie worked on it. Brendan McCormack started this off in about 2000 of using these wall stations. Who's familiar? Anyone seen those or seen the idea? Of course, you know, traditional surveying, we've got the backs which are now 50 metres up in the air. You can't put a point on the ground because they're going to run over, it's going to get covered over. At one stage we used to bolt a bracket onto the wall of the mine and then set the total station and the targets up on those permanent fixtures. And then a couple of, back in about 2000, they said, well, we've got these prisms from Leica which have a zero, doesn't matter which way they point, you'll always be centred. So no matter what the orientation, you're measuring to the centre of the prism. They put a stem, so it's about 200 millimetres from the stem to the centre of the prism, and then they drilled a hole in the wall, put a tube in it, and you slip the stem into the tube. And so you've got survey control. You do a free station survey where you set your total station up anywhere you want to, take a couple of back sites, and with resection you know where your total station is, so that then you can fire forward to one of these and determine the coordinates of that point, and so you can continue your control down your mine using wall stations. Next time you want to come back and do some more survey work, you slip a couple of these prisms on their stems into the wall station, set up a free station, resection, and away you go. And this is a very popular method of doing it now. Well, you know, it's almost 20 years old now, I suppose. But my question, and the mining rules say, when you close a mine down, you have to have the coordinates of your control points. Now, is the mines department going to accept something stuck out on a stem? This is about the only configuration going at the moment. Are they going to accept those as the coordinates, or do they want the coordinates back here at the sleeve? That's the question that no one's asked yet. I talked to a mining surveyor the other day who's not mining anymore, and he said, no one's asked that. So I've just gone around and worked out a method of actually transferring the coordinates back to the wall sleeve, and I've got direction cosines which just tell me in 3 dimensions which way the coordinates are going. So if I know that, say that's my wall station, or I survey that one in, take a reading there, and it's 200 millimetres through the sleeve, and I've got another 400 millimetres up there, because I know where I am with my total station, it's oriented, I know where those two are, then I can basically slide that prism down here to this point, which gives me the coordinates of the point, but solving that triangle also gives me the directions of it. So I could come back in a couple of years' time and slip another stem into it with a different prism, and using those coordinates and the direction cosines, regenerate that position. And that's just, I've put this up, I've written it up, and you're the first blokes to see it, and I don't know whether it's really of any interest to anyone or not, but they're the sorts of things that I've done. And so all this goes into the book that we're producing because it's basically impossible to find this anywhere else. So I've Schofield and Breach, one of the engineering books has got it. The other one I'll go back is to F.A. Shepherd, who was teaching in England, and he's the only one, this is in the 60s, and 1968 was one book and 1981 was his second book. This is the only thing that works on dip and strike that I've seen, apart from half a page in Schofield and Breach. So there we are. People I have known. Graham Sands, I met him a year or so before he was killed at the Canning Dam when they were chasing GPS satellites. Peter Livings, he ran the photogrammetric company, and he was processing data for Aerodata because they used to have an 8mm camera in the bottom of the aircraft, and every time they took a magnetometer reading, they took a photograph with the 8mm and transferred it to aerial photographs, and then Peter got the coordinates off the aerial photos so Aerodata could put them back into their mag maps. Peter Clifford, I've worked with him. Tim Gill worked with Peter, this is back in about 95, 96. Yeah, they're the people that I've worked with. I was up at Norina Downs in the 60s and 70s. General Mining Corporation were looking for nickel there. Tasmanex found 5% nickel at Nullagine. Luckily I was in Perth at the time when they found it, so I was able to get rid of a lot of shares because I think they found the nickel on the Friday, and I think on Tuesday the blokes were in jail. So, and to say the introduction, carboid minerals, so I helped them get a Land Rover going, and so I said I was going to leave the bush and come, you know, do surveying, and the guy said, oh, well, thanks for looking after us, and sent me Clark Volume 1 on surveying, and that's where I started in surveying. The one thing I was doing, I mean, surveyors now, you've got so many tools, you've got so many programs that you think it's all automatic, and it is. It's the only way we can handle the workload, but you have to get back to the basics of how it works, because once you understand how it works, then you can go forward and work with this stuff. And I was just said tonight, or part of the presentation was going to be, you've got a guy flying an Airbus 380. He still went down to Jandakot or wherever, and he hopped in his Cessna, his Piper, his Jabiru or whatever, and he started to learn to fly, and he flew in the air. He started right at the basics. And I've got these guys for 12 lessons. I could get a 16-year-old kid, relatively competent, get him flying solo at Jandakot with all the ratings that he needs to do that as a student pilot within 12 lessons. So, you know, hopefully our mine guys are, you know, as good as that, and I think the level of stuff that we're pitching to them is about the level of the, you know, learning to fly. And that's, I'm a great believer in knowing the basics. Once we've got the basics, then we can move forward, and so the book is all about basics. Thank you.